Alright, so in this video I'm going to show you a step-by-step build of a demonstration circuit for the inverting comparator using a 741 op amp. I have it right there. There's the pin layout for the 741 op amp. It's pretty simple though. Primarily we're worried about these three. So hopefully you already know about the non-inverting comparator using an op amp, because it's really the same circuit except for polarities are reversed. So I have the exact same diagram except for I changed a few things compared to my non-inverting comparator. So in this case, now we have the inverting pin as our control pin. Before we had the non-inverting pin up here. I just swapped them out. We're going to ground the non-inverting pin and our signal's going to go to the inverting pin. So right up here you can see which pin for the 741 op amp I'm talking about. So any positive voltage value will give us a negative voltage coming out, and that's going to be saturated. So it's just going to be an on-off switch basically, except for it's either going to be negative voltage or positive voltage, and we'll look at that later. So now with the same setup as over here, if we give it a negative voltage at the inverting pin in relationship to the non-inverting pin, which we're going to ground, then we'll get an output of a positive voltage. So to begin with, we're going to focus on the op amp and we'll power it last. So we're going to set the ground to the non-inverting pin. So it's important you know which pin that is. It is pin number 3 for the 741 op amp that I am using. And what I'm going to do, this is going to be my ground point, my 0-volt reference point. The two batteries are going to come to that point. I'm going to take a 2 kilo ohm resistor. The value of resistor doesn't matter. We could even just attach a wire directly to it, because ideally the op amp doesn't allow any current through its input pins. But I like having the resistor in case I short circuit to something next to it or something. We have this resistance to limit current flowing somewhere else. So now we're going to hook up the pin that we're going to send our signal to. As I said, that's the inverting pin, which is pin number 2. I'm going to use this trim pot. It also has resistors over here, but it's a voltage divider, but I can only adjust it this far, so we'll get about 4.5 volts positive to about 4.5 volts negative. So I'm just going to take a jumper wire and I'm going to leave some space so I can get an easy multimeter measurement there and plug it over to here. So I'm not worried about current. All of the current's going to flow through here, but it will be able to measure the voltage at pin number 2 with no problem, but no current will pass through there. So now we're going to add the output, and this is really just a visual to help you see the output here. So we're going to need a resistor. So I'm going to use a 470 ohm resistor. That's about the minimum you want to use when you have 9 volts. It's either going to be a 9 volts positive or a 9 volts negative. That's in relationship to ground. So there's only going to be about a 9 volt difference, not an 18 volt difference as far as ground's concerned. So this is going to be a polarity indicator. It's going to give us a good visual of what's going on when it comes to voltage and current. So the green LED I'm going to set so that it conducts when the output's more positive. So if the output's more positive, then a current will flow through the resistor, and then the green LED. So I'm going to put the longer lead closer to the output of the trim pot. Shorter lead I'm going to put to ground. Shorter lead's the cathode, longer lead is the anode, and of course the red LED I'm going to do the opposite. So the long lead, the anode, I'm going to put to ground, shorter lead the cathode, because when the output's more negative, that will allow the red LED to conduct. And so plug it into the same 2 rows there. So 1 row above ground, we're going to add a 470 ohm resistor and connect that to the output of the trim pot, which is pin number 6. So I'm not going to keep showing the pin layout that's at the top of the sheet. So I'll just put that in 6. Trust me that it is 6. And I stuck that in the wrong row there. So make sure when you wire these you recheck where everything's inserted, because it's really easy to insert the leads into a wrong row and then wonder why it's not working when you're done. And now we're going to power the circuit. So I'm going to use two, technically they're kind of called 9-volt batteries, but they actually only have about 8 volts, even though it says 9 volts on there. They're rechargeable though, so that's really nice. And so the ground is going to be this spot right here where the two batteries come together, and then there'll be a current path one way that way, and then an electron flow path that way for a negative voltage. So in any case, I'm going to plug in the red wire there for this battery, and these are stranded wires, so it's not a bad idea to twist them before you put them in. I haven't found battery snaps yet with solid wire yet, but this really doesn't want to go in. So twist those up even more, and be careful pushing them in. Don't force it, just try to wiggle it, try to let it slide through. And then the other battery here, I'm going to do the black wire to the blue row there, the negative rail. And as you can see, I got jumpers at the bottom that connect the blue to the blue and the red to the red. And so once I plug both batteries into the ground rail, then we'll have 19 volts, or almost 18 volts I should say, closer to 16 in reality, across the rails. And the leads don't want to go in today, so that happens sometimes. Alright, so the red LED's on, but that will likely change when we plug this in here. So now, as I said before, we have the green LED set to light up when the output is more positive. The trim pot here is set towards the more negative side of the power rail, so I'm going to turn the trim pot towards the positive side of the rail. Now we just output a positive voltage, a very low one. Even as I turn the voltage up, the brightness of the LED doesn't change because the output is saturated, either more positive or more negative than ground. And now we'll take a look at the voltages. So all voltages are going to be in relationship to ground, as I said before. So I'll just kind of permanently attach the black probe there. I'm going to hold it though. And you can see we got, remember before I said we could get to almost 4.5 volts positive. If we were using actual 9-volt batteries, it would be closer to 4.5 volts, but these are closer to 8. So now I'm going to set this closer to, or first let's do the output voltage. So we got the red LED on. I said when the red LED is on we should expect a negative voltage, and there you can see negative about 5.4. So now I'm going to set this almost halfway, but I'm going to stay where this is in positive territory. And there again you can see we got a positive voltage at the output of the trim pot, and at the output of the op amp we have a negative voltage. So actually we have a positive voltage to the inverting pin, so we have an inverted voltage at the output. And you can see the voltage is the same at the output, even though I changed the voltage at the input. It just saturates right away. And so now I'm going to just barely set it to a negative voltage, which we'll verify right here. So negative about 0.5 volts. So that's the input for the inverting pin. And there now you can see we have a positive voltage here. And the voltages don't match up. I thought they would, but maybe it's because I'm using an op amp instead of a comparator. I don't have a comparator though, so I'll probably buy one and see if we get the same voltage, positive and negative. But here now we're a lot more negative voltage, and still it's the same voltage at the output. It's positive. So the output's positive when the input's negative. That's the main takeaway for the circuit. And so now we really did all we can do with the circuit. We want to make sure we remove the batteries, because especially when you have a resistive voltage divider like this, there's always going to be current flowing through there, so the batteries are going to drain if you leave them plugged in. You're guaranteed for it to drain. So now we come to this little graph, and I did the same graph with the non-inverting circuit. The non-inverting circuit was practically the same, except for you had the same output voltage wise as input, either positive or negative in that aspect. So for the inverting signal though, when you're in the positive range, then for the input, then the output is in the negative range, and vice versa. Once you dip down to negative, it jumps right to the positive range, and it saturates. It gets to the maximum voltage it's going to get to, and that keeps happening each time you flip. And even if you waver around quite a bit within the positive range, as long as you stay up there, you're going to stay in the negative range, and vice versa, dip down to negative. So these graphs, a lot of people, they show how voltage changes in different areas of a circuit are going to affect another area of the circuit with graphs like this a lot. So it's a good idea to get used to reading them, and this one's a pretty easy one to understand.